Alright, we want to start finishing up some of the IB particle physics material, and the first thing we want to talk about is what's called quark confinement. So quark confinement is one of those things that ends up on the IB exam as like a 1 mark or 2 mark question, and it's a minor theoretical point, but it is something they have asked about quite a bit. And the gist of quark confinement is that you cannot isolate a single quark. They are always going to be observed with other quarks. So the first thing is, and the other thing is, sorry, let me rephrase that. Basically, you can't just have a quark on its own. It has to be part of a particle. So we would say that they only exist in hadrons, whether they're a meson, which contains a quark and an antiquark, or a baryon, so there's something that has 3 quarks. So we can't actually isolate quarks, and this is what we call quark confinement. And basically, we're just saying that quarks are going to be confined to a particle always. And the reason for that, it just comes from a little bit more advanced particle physics theory. But basically, we kind of look at the case like if we have a meson, so we have a quark and an antiquark. And what we're trying to do here is we're trying to input energy in order to separate the 2 quarks. Because to do that, you will need to put energy in. What's going to happen eventually, though, is the system, it's going to be much more energetically favorable to produce a new quark and antiquark pair rather than to continually separate the original quark and antiquark. So what's going to happen is in this more energetically favorable configuration, a new quark and antiquark are going to be produced, and then what's going to happen is we're going to get 2 mesons out of this instead. And each of these mesons is going to have a quark and an antiquark. So any attempt to try and separate the quarks, we're actually just going to end up making new quarks out of this. So we can't actually separate or isolate quarks. And that's the gist of what quark confinement is. What we want to step into now is this thing called quantum field theory, and we're really going to go to town on this when we start talking about Feynman diagrams in the next few videos. But by the time we hit to the 1930s, so we had some big physicists like Dirac, Heisenberg, Born, and they had established this idea of quantum field theory. So what they were doing is they were combining relativity with quantum mechanics. And the big thing of this theory is they proposed this idea of mediating particles. So the whole job of a mediating particle, it's meant to be what we call a carrier of one of the fundamental forces. So we have mediating particles for the electromagnetic force, the strong nuclear force, and the weak nuclear force. There is a hypothesis about the mediating particle for the gravitational force. They just haven't been found to exist yet, at least experimentally. Now these are also referred to as virtual particles just because these mediating particles, they exist for a really brief period of time. So they're really, really hard to detect. Now, we just kind of want to look at an example of how these mediating particles would work, and we're using a very oversimplified example here. So for example, I have these 2 people, they're standing on like a slippery surface and they're throwing a ball towards one another. Let's say it's a medicine ball because those are nice and heavy. So each time this person, so let's say this woman, she's throwing this ball to this man. So when she throws it, she's going to apply a force on the ball. So she's going to push it towards the man. But at the same time, we know from Newton's third law that this ball is going to push back on this woman and she's going to slide back. Now, when this man catches that ball, he's going to go sliding back. We can look at that through like a collision or conservation of momentum. He throws it to the woman, he's going to push it right, the ball is going to push back on him to the left, and he's going to move. So each time this pair throws the ball back and forth, they're going to start to continually move apart. What we would say in this example is we would say the 2 persons, they're acting like every ordinary particle, and this ball, it's acting as sort of a mediating particle for repulsion. It's pushing them apart, and this ball is carrying the force that's pushing them apart. We could also look at that from an attractive point of view. So in this case, it's the same 2 people, they're standing on the ice, but this time they're holding something really sticky. I think where I got this from, they're holding a sticky candy apple. Why they'd be doing that, no idea. We're not going to question that. But every time the one person tries to grab at the apple, it's really sticky, so it's going to pull them a bit closer to the other person. Then the other person is going to try and grab at that apple, it's real sticky. They're going to pull each other close together. So again, these 2 people, they are acting like ordinary particles, and that sticky apple, that's acting as sort of a mediating particle for this attractive force that's going between them. So that's kind of the overall gist of mediating particles. As we said, that the analogies we've used are a huge oversimplification. If you end up studying quantum mechanics or quantum field theory, you're going to realize it's extraordinarily complex. Now, the mediating particles we like to talk about aren't medicine balls and sticky candy apples. We actually have proper names for them. So, in the 70s, high energy particle accelerators determined that the strong nuclear force is actually carried by this particle known as a gluon. So the gluon is the mediating particle for the strong nuclear force. To oversimplify the gluon's role, we kind of think of it as like the glue or what holds quarks together. That's kind of what that's what we mean when we talk about gluons. But again, for those of you that are a little bit more advanced in physics, I realize and admit that's an oversimplification. Later, it was discovered that for the weak nuclear force, we have 3 different types of mediating particles. We have the W+, the W-, and the Z0 bosons. Which boson gets used is going to depend on the type of interaction. And when we study Feynman diagrams a little bit later, we're going to talk a little bit more about those. We haven't talked about it explicitly, but photons are the carrier of the electromagnetic force. And then the last of the 4 fundamental forces we haven't really discussed in terms of mediating particles is the gravitational force. So in theory, it has a mediating particle known as a graviton. So the graviton would be the carrier of the gravitational force. To date, in 2020, we don't have any experimental evidence that suggests their existence. Does that mean it doesn't exist? No, it just means we haven't discovered it yet. If we discover it, great. If we can show evidence that it doesn't exist, then of course, like everything in physics, we'll adjust our theories accordingly.